Hey guys, welcome to the Basics of Circuits video. As you may have gathered from the introduction, turns out we are not done with the subject of capacitors. Because, let's be honest, the way physics works, you're never really done with anything. It's all cumulative. Now, in the unit, in this unit, we're going to learn about a bunch of different circuit elements and also circuit notation. So to begin with, I thought I would introduce these three symbols that you see before you on the screen. These are the only ones that we're going to use this year. We're not going to learn about other things such as diodes, inductors, those kinds of things. So there's lots more circuit elements out there, but these are the main ones that we will deal with just for starters. Now you can connect these various circuit elements up in a variety of different ways. I've ignored the battery for this, but the main ways of connecting things are either series or parallel. So series circuits always involve two things being on the same wire. So as you can see, there's only, if I were an electron traveling through this circuit, traveling through this network, I could also say, there's only one way to go, right? Series means there's only one path, meaning if I go through this resistor, whatever that is, we haven't learned about those yet, then I also have to go through this resistor. All right, if we're talking about charge traveling through this, right, charge would have to go through this and then this. All right, and then same story here, okay, because there's only one path to follow. Parallel, by contrast, always involves two paths because of what's called a junction. Now, none of these things I drew here are really complete circuits. Okay, I didn't draw the battery that they're presumably hooked up to, right? If I hooked up, say, this one to a battery, that might go like there, right? It's now a complete circuit. Fine. But a junction is a point like this one right here, or also, for that matter, this one right here, where the wire splits, okay? And then if we're talking about charge flowing through a circuit, which is going to be a big thing that we will talk about, is charge moving through it, that's going to be a point where the charge either has to split or come back together, all right? So all three of those show junctions. Junctions don't have to only go two ways. You could have, obviously, a more-way junction, okay? Right, you could have, there it splits off three ways and resistor, okay, whatever, right? And then it comes back together. So it can split three ways, four ways, whatever it may happen to be. So let's do a quick quiz on recognizing which of these networks has capacitors that are connected in series. Pause the video, give it a think. And now that you've thought about it, A is definitely in series, right? Like we discussed in previous moments of this video, yeah, those two, that's just like the drawing that you had before. Those are clearly in series. They're on the same exact wire, right? There's only one path around this circuit. C is definitely parallel, all right? So don't pick that one, right? There's definitely a junction there. But B, a lot of the time people fall for this one. They think that one's in parallel because of that word parallel, right? They see parallel wires right here, and they think that the word parallel in parallel circuits means that you must have parallel lines, and that is not at all the case. In fact, the presence of parallel lines is merely an artifact of the fact that I drew things on a square. There's no junction. There's only one path around this circuit. A corner is not a junction. There's nothing even kind of special about a corner, and frankly, corners don't exist in real circuits. It's just a bunch of loose dangly wires behind the walls. All right, so this is actually a series arrangement just like A. Don't be fooled. Parallel lines doesn't mean it's parallel. What you'll look for is the junction. If there's no junction, then it's not parallel. So now another quiz time thing. Based on what we hopefully learned with the last one, I'd like you to draw a circuit, including the battery, where all three capacitors are in series, all three capacitors are in parallel. All right, so pause the video, try it out wherever you like. Okay, here are a few of the solutions. If you think you've drawn it another way that doesn't look the same, but you think is probably the same, feel free to send me a picture of it, and I will evaluate it for you, tell you if it's right or wrong. And now try part C. Draw two other unique arrangements of capacitors. Meaning, use three capacitors, have a battery in there, but they're not all three going to be in series or in parallel. All right, so pause the video, try and come up with two other unique arrangements. Now, you may have drawn several different things that actually end up being identical. So I've shown you, here's a group of three that are actually identical, right? Those are not different from each other. They're drawn differently, but they're not actually different, okay? And then same idea here, right? There's two possible ways of drawing that arrangement. By the way, I am in drawing this presuming three equal capacitors. If the capacitors have different values, then obviously you could have different arrangements by just, switching the position of two capacitors. Okay, whatever. But if they're all three equal capacitors, then these are two other possible arrangements. Now this brings us to the whole point of this, really, which is what we want to be able to do is to, quote, analyze a circuit. When you analyze a circuit, what you are doing is figuring out the charge and voltage on each of the capacitors in it. Or when we start talking about resistors, then we'll talk about the current and voltage. Whatever, you don't know what current is yet, that's okay. But the charge and the voltage on each of the capacitors. So every circuit can be analyzed using Kirchhoff's laws. So I'm phrasing them here maybe slightly different from how we'll do them later in the unit, because we're going to use them for capacitors first. So his first law says, the sum of the volts equals 0 for any closed loop. Oh, what the heck does that mean? Well, what it means is, if you've got, say, a 9-volt battery, it means that 9 volts is going to get closed, or is going to get used, rather. It says, for any closed loop. All right, meaning if the battery provides 9 volts, then 9 volts are going to get used up around what's called a loop. All right, now what is a loop? A loop is a path around the circuit. Okay, so when we say a closed loop, it means a path that ends where it starts. All right, so this would be a closed loop. All right, this also is a closed loop. And for that matter, I could do another, closed loop around this way. Okay. All right, fine. So those are all different loops. Now, what that means is this: if the battery provides 9 volts, and let's say this capacitor happens to be using 2 volts, how exactly you would figure that out, we will talk about, say, later in the unit. But if that's using, like next lesson, if that's 2 volts, well then this next capacitor over here must be using 7 volts. Why is that set? What about the other capacitor? Hold it, just bear with me. If on this loop here, I've only got my battery and my 2 capacitors, between those, they must be using 9 volts. So if this one's using 2 volts, then the other one must be using 7. Okay. The other capacitor that I neglected, though, is also using 7 volts. If you're thinking to yourself, well, that sounds just bonkers. Well, consider this path. Around that path, 9 volts must get used. So, again, if this one's using 2 volts, then this must be using 7 volts in order for 9 volts to get used up altogether. All right, the secret to this working is this junction right here. All right, that junction, well, or this junction, either way you want to look at it. The junction means that those two capacitors are in parallel, the two that are using 7 volts, right? Since they are in parallel, they receive equal voltages. All right, so that's the rule. Parallel branches receive equal volts. Regardless of whether we're talking about resistors or capacitors or anything else, parallel branches always receive equal volts. And definitely write that down somewhere. Super important. So if you had a simpler arrangement, where let's say they were all 3 in series, like this here, none of these capacitors get 9 volts, not a single one. If, the first one gets 3, and the second gets 3, and the last one gets 3, that's okay, but it could also just as easily be, say, like 1 volt, 6 volts, and 2 volts, and that's okay because that adds up to 9. That brings us now to Kirchhoff's second law, which is charge in equals charge out for any junction. So what this is referring to is, well, it says for the junction, right? So at that junction, and also at that junction, right, there's a certain amount of charge coming into it from the battery. At that point, I mean, let's say that's 1 coulomb, just for the sake of argument. At the junction, some of the charge must go this way onto that capacitor, and some of it must go this way onto the other capacitor. All right, and then things join back up here, and there we go. All right, but for parallel capacitors, therefore, while they have the same volts, they don't necessarily get the same amount of charge, which is okay because remember, C equals Q over delta V. So if they've got different capacitances and the same voltage, then they would definitely get different charges on them. On the other hand, when you have 2 series capacitors, you get something that seems a little bit confusing, which goes like this. If you've got some total amount of charge coming out of the battery, it accumulates on this capacitor and also on this capacitor. Both. Both capacitors get the same charge, regardless of whether or not they have the same voltage on them, which, if they're different capacitances, they definitely will not have the same voltage on them when they're in a series arrangement. So there's our next really important thing to write down. Series capacitors receive equal charges. That one's a weird one, so let me explain. It works this way because when charge comes out of the battery, it initially only actually accumulates on the first plate here. So if, let's say, that's positive charge on that plate, there will end up being negative charge on the other side. But if you think physically about where that would have to come from, it has to come from the plate next door. All right? And if it was losing negative charge to put onto the other plate of the first capacitor, well, then it must itself acquire a positive charge because it lost a certain amount of negative charge. All right, you can imagine how this is going to go. That will induce a negative charge on this plate, which it acquires from the other plate, which therefore accumulates a positive charge, and then this plate gets a negative charge by pulling in negative from the battery. All right, so in the end, the amount of charge on each of those series capacitors is exactly the same. All right, so here's our executive summary of how capacitor networks work. Pause the video, write this down. This is very important, and we will continue talking about it in the next video a lot.